Hello everyone, my name is Xinze and I'm from Tsinghua University. It is my great honor to give a talk on our work, fooling an unbounded adversary with a short key repeatedly, the honey encryption perspective. This work is in collaboration with Professor Tang from the University of Sydney and Professor Zhang from Chinese Academy of Sciences, and is presented in ITC 2021. Our work is inspired by Shannon's fundamental work on perfect secrecy. Shannon proved that a simple and elegant construction of one-time pad satisfies perfect secrecy, which hides all information of input messages. However, one-time pad is hardly used in practice. There are two well-known reasons. The first is key length problem, which says we must use a key as long as the message. The second is key reuse problem, which says we must not use one key to encrypt more than one message. Shannon also showed that these two problems are unavoidable as long as we are working in perfect secrecy. In order to overcome these two problems, researchers have been working on more practical security notions. One of the most important branch of work is computational security, where the attacker is assumed to be polynomially bounded. Solutions to the key problems become simple in computational settings. For example, we can use a pseudo-random generator to stretch a short key into a long one, and we can use a pseudo-random function to encrypt multiple messages with the same key. However, there are times when we prefer to stay in information theoretic settings. A natural question is, can we also solve the key problems against unbounded attackers? Considering Shannon's negative results on perfect secrecy, it is natural to look for other security notions, which only work in certain scenarios. A noticeable solution of using a short key in information theoretic settings is the entropic security notion. Entropic security is somewhere between perfect secrecy and computational security notions. It hides all partial information against unbounded attackers. It also has restrictions on inputs, that is, the input must have high entropy. For an n-bit input with entropy k, entropic security requires a key of length n-k. This implies entropic security does not work well for low entropy inputs. For example, if the input only has half entropy, then it would require a key as long as the input. Therefore, we need to look for other solutions that can deal with low entropy inputs. Entropic security suggests that if we add restrictions to the input, then we may be able to use shorter keys. A natural question is, can we give different restrictions to the input and come up with a new scenario where we can use a shorter key and probably reuse the key at the same time? After some research work, we find honey encryption might be suitable. In honey encryption, the input distribution is specified and publicly known to everyone. This restriction is in some sense less general than entropic security, but there is no entropy requirements, and therefore honey encryption performs better than entropic security for low entropy inputs. Honey encryption was originally designed to achieve best possible security in password-based encryption. Human-chosen passwords tend to be weak, and a strong attacker may perform a brute force attack on all possible passwords. This strong attacker is modeled to be unbounded in previous works. Upon receiving a message, the attacker can decrypt it using all possible passwords. It is easy to find the correct password in this way, since decryption using the correct passwords results in meaningful message, while decryption using wrong passwords often gives random results. It has been shown that we cannot guarantee security for arbitrary input in these settings. Rather, security can only be achieved for a specific input distribution. The seemingly negative result on honey encryption becomes not so negative if we look from a different perspective. That is, we consider honey encryption as a way to encrypt a specific distribution. Honey encryption now becomes an information theoretic encryption, which works on this specific input. What's more, it also uses a short key, which corresponds to poor human-chosen passwords. As a result, honey encryption can be viewed as an information theoretic encryption scheme, which already uses a short key. Let us look deeper into instantiations of honey encryption schemes. There is an important building block called Distribution Transforming Encoder, or DTE for short. This encoder works as a normalization of input distribution, which is assumed to be publicly known in the setup phase. This is important since one DTE only works for one distribution. Upon receiving input message, DTE outputs an encoding with near-uniform distribution. In other words, the distribution of the encoding is statistically close to uniform. Such encoding scheme can be efficiently constructed if input distribution is explicitly given, which is the case in many real-world applications. For example, genomic data or natural languages. With the DTE building block in mind, honey encryption schemes can be constructed in two steps. The first step is to perform DTE on input message, and the second step is to use a symmetric encryption scheme on the encoding. As an example, the symmetric encryption scheme can be instantiated using a hash function. In previous works on honey encryption, this hash function is modeled as random oracle, which is important in security analysis, as we shall see later. This two-step construction, which is called DTE-then-Hash, is a standard framework to construct a honey encryption scheme, and is proved to achieve the security goal we are about to define. We now move on to the security definitions of honey encryption. The very beginning work on honey encryption only considered a weaker security notion called message recovery security. Follow-up work proposed a stronger notion called target distribution semantic security, which aims at hiding all partial information of input, as it is in perfect secrecy and entropic security. This is also the security definition we are working with. Target distribution semantic security is defined via two security games. In both games, input distribution is made public. In Game 0, the adversary learns an encrypted message and tries to guess the value of a predicate f on original message. And in Game 1, a simulator learns nothing but still tries to guess the predicate. Security is defined to be the maximum of all advantages Game 0 has over Game 1, where the maximum is computed over all predicates. The DTE-then-Hash construction has been proved to satisfy target distribution semantic security in previous work, but it involves a very complicated analysis. Let us take a brief look into this analysis. The first step is a series of game transitions. In the final game, the adversary's best strategy is to perform a brute force attack on all possible keys, decrypt using each key, and see if the predicate is more likely to be 0 or 1. The second step is a balls into bins analysis. There are two bins, 0 and 1, indicating predicate value, and each decryption is considered as a balls throw. A majorization step is also needed to normalize key probabilities. What's more, both majorization and balls into bins analysis require random oracle to guarantee independence. A natural question to this random oracle-based analysis is, can we get rid of random oracle and prove security in standard model? As we mentioned, there are two major challenges. First is we cannot perform majorization on correlated random variables. And second is we cannot consider each ball throws to be correlated in balls into beans experiment. The whole experiment does not make sense anymore. We did come up with a possible modification to this analysis. We can replace random oracle with a qwise hash function, and the balls into beans analysis and majorization step can be avoided by bounding tail probabilities of correlated random variables. However, the modified analysis still involves very complicated mathematics. Furthermore, in order to get a reasonable security bound, we may need to choose Q as large as security parameter. In contrast with previous complicated security analysis, we propose an alternative analysis which is extremely simple yet unnoticed before. The idea is to use entropic security, which also hides all partial information, as it is in honey encryption. The only difference is that, in entropic security, we are dealing with high entropy inputs, and in honey encryption, the specific input distribution may not have high entropy. Therefore, our goal is to map this specific distribution to a high entropy one. To begin with, let us recall the properties of DTE, that is, it encodes input message into a near uniform distribution. Now, our observation is, this near uniform distribution also has almost full entropy. In fact, we can consider it to be a uniform distribution with full entropy, which only adds negligible error. In this way, we can apply an entropically secure encryption to this uniform encoding. And entropic security always holds for full entropy input. We can then show this construction hides all predicates of original message, since the entropically secure encryption hides all predicates of DTE encodings, and every predicate of original message is also a predicate of the encoding. To instantiate the entropically secure encryption, we use a pairwise hash construction. In this way, we exactly recover the DTE-then-Hash construction. The only difference is we are now using pairwise hash function instead of random oracle. As a result, we have shown the DTE-then-Hash construction achieves target distribution semantic security using pairwise hash function, while previous analysis requires using qwise hash function for a rather large queue. This instantiation is much easier to analyze, and it even achieves a slightly better security bound. Now that we know honey encryption achieves information theoretic security while using a short key, we would like to present a comparison among perfect secrecy, entropic security, and honey encryption. Perfect secrecy is the most general in terms of input. It works for any input distribution, but it also requires the longest key, which is as long as the message. Entropic security works for any high entropy input, and uses a shorter key depending on input entropy. Honey encryption only works for a specific input distribution, but uses the shortest key, which is actually independent of input entropy. We now turn to the key reuse problem in information theoretic security. As we shall see, entropic security uses a short key, but unfortunately, it cannot reuse the short key. This is because entropic security requires randomness from the key to fill in the entropy holes in messages. Encrypting one message with n-k entropy requires k bits of fresh randomness from the key, which quickly adds up if more messages are encrypted. For example, encrypting T messages would require T times k bits of randomness from the key. A single short key cannot afford such amount of randomness. Since honey encryption uses entropically secure encryption as ingredient, it is straightforward to argue that honey encryption does not support key reuse in general. However, there is still chance if you use a specific instantiation of entropically secure encryption. This is because we are actually feeding a uniform distribution to entropically secure encryption, which might be secure if the input is always uniform. In fact, we will show the DTE-then-Hash construction using pairwise hash function indeed supports key reuse. It is worth noting that not all entropically secure encryption schemes support key reuse when input distribution is assumed to be uniform. Only the pairwise hash construction is known to satisfy this property. Before we proceed, we need to give a definition of target distribution semantic security for multiple messages. It is similar to a single message case, but different in some places. In the setup phase, we assume the messages are sampled from the same distribution independently. Now in game 0, the adversary receives encryptions of every message using the same key, and in game 1, the simulator receives nothing. The predicate to be guessed is now defined on the vector of all messages. Security is still defined to be the maximum of all advantages game 0 has over game 1, where the maximum is computed over all predicates. Unsurprisingly, security of DTE-then-Hash construction in multiple messages settings can be reduced to single message case. The observation is that DTE encodings of multiple independent messages still results in a near-uniform distribution. If we combine the n messages into a large message vector, we can get a DTE of this vector by performing DTE on each piece of message separately and then combining the outputs together. Furthermore, combining n pairwise hash functions together still gives a pairwise hash function. In this way, security in multiple messages case can be proved using the results in single message case. To sum up, we propose a brand new view of honey encryption scheme from the perspective of information theoretic encryption. Previously, honey encryption is only an approach to achieve security in password-based encryptions, and is forced to specify message distribution. However, we claim honey encryption is a good solution if our initial goal is to encrypt a specific distribution. Although exploring message distribution in some sense sacrifices generality, it actually enables us to use a short key repeatedly, which serves as a possible solution to the two weaknesses of one-time pad. Last but not least, we are also left with some thoughts on information theoretic security. One question is, does exploring message distribution make information theoretic encryption useful in practice? There are scenarios where the message distribution is already known to everyone, but there are other cases where revealing message distribution might be risky. Can we still use information theoretic encryption in these cases? This also leads to another question. Is there any other possible trade-offs between generality and information theoretic security besides restricting input distribution? For example, the bounded storage model uses a public random source, which broadcasts random strings non-stop. There might also be other scenarios where information theoretic security can be achieved under other assumptions.